So now let's go into the first law of thermodynamics proper. As we stated earlier, the description of the general form of the first law is delta U is equals to Q plus W, or delta U is equals to Q minus W. The differential form of the first law of thermodynamics is always correct, and there's only one form of writing it. That's du is equals to dq plus dw. We use the lowercase delta, okay, to denote that heat and work are not state functions. Now, remember a couple of lessons back, we talked about how as long as we knew the number of moles, we are going to be able to figure out what the third variable is by knowing what two variables are. So for instance, we are going to be able to know what the internal energy of a system is purely by measuring its pressure and volume if we know the number of moles. This is not applicable to state functions. You cannot figure out the amount of heat in a system, all right, by knowing the number of moles and knowing pressure and volume. Now, throughout this lecture and indeed this entire course, we use the following notation to differentiate between properties of a total system and the properties per unit mass. Often in thermodynamics, we are very concerned with the properties per unit mass. And when we do that, we use the underscore. So for example, if we wanted to find out the internal energy per unit mass, we divide the total internal energy by the number of moles, and that gives us the total energy per unit mass. The same notation applies for volume. You can take volume divided by mass, and you know it's volume per mass, or specific volume. The term to remember is specific. So now, density is the reciprocal of the specific volume. Therefore, specific volume is essentially 1 over rho. Remember that rho is equals to mass over volume. Therefore, volume over mass is equals to 1 over rho, and volume over mass is specific volume. So, what is an open and closed system? So far, we've been dealing with closed systems. Closed systems essentially have very fixed boundaries. For instance, this box over here with particles moving on the inside. In an open system, we must take into account materials going in and materials going out. When we calculate changes in an open system, we have to first define an imaginary boundary here, or wherever it is you have to take note of it in the system. And your equation must include the amount of materials going in and going out. Now, let's look at an example of an open system. This is a classic open system where you've got materials, energy being transported into the system in the form of V in, and energy being transported out the system in terms of V out. We consider this system in equilibrium, which means that the amount of materials going in is equal to the amount of materials going out. This system, however, drives a fan or a shaft. How do we increase the amount of energy to drive the shaft? We, of course, add heat. Let's look at another example. This over here is another system driving a piston up and down. In this example, it's an open system. You've got mass going in and you've got mass going out. Imagine this as a constant flow of water, perhaps. You can increase the speed of this shaft by either heating the water or using a turbine blade, perhaps, to increase the amount of work that goes into the water. So hence 1.12 is actually a good description or the description for an open system. Don't be scared by this equation. What this equation really is doing is assuming that the description of the total change in energy of the system is the amount of materials going in minus the amount of materials going out plus a change in heat and a change in work.